Okay, we're going to talk about buffer solutions and titration curves. And first will be buffer solutions. Okay, and these are solutions, aqueous solutions that resist a change in pH when small amounts or a small amount of acid or base or water is added. Okay, so that's a definition of a buffer solution. How do you make a buffer solution? Okay, an acidic buffer, hopefully you can deduce that that is with a pH less than 7, okay, is made by combining a weak acid with a salt containing its anion, okay, or its conjugate base. All right, so, or you could also mix substances so that you end up with some acid and its anion in solution. For instance, if I have acetic acid, okay, the buffer would look like this. This would be your buffer system. Okay. Now, the idea is you pretty much have equal molar solutions of your anion and your base. Okay, so equal molar. Concentration is the same. All right, your capacity of your buffer is how much acid or base that it could absorb and still maintain the pH, because you can go past the capacity and drive the reaction either to the acidic side or the basic side. Okay. Basic buffer, very similar. Your pH is going to be greater than 7, and you're going to make this by a weak base, making a solution of a weak base plus its cation. Okay, and again, equal molar is typically how buffer solutions are made. Okay, and the idea is you want to set up that equilibrium back and forth. Now, to do buffer calculations, there's a couple of things to look at. Again, if you add acid or base, you're going to do the neutralization reaction first. Decide what is in the solution. Calculate concentrations. Calculate concentrations. And then set up the equilibrium and do whatever equilibrium calculations are necessary. Okay. Now, there is one equation that you can use. Again, if we use that acetic acid buffer, you should remember that your Ka is your concentration of your CH3 ion and your hydronium ion over the concentration of the acetic acid. Okay. If I take the logs of both sides and rearrange, I will end up with the equation pH is equal to the pKa plus the log of the concentration of the salt and the acid. Okay. If the concentration of these two things are equal, this will drop out and your pH is equal to your pKa. On a titration curve, you would have a weak acid, okay? Your buffer region is here. And the point here is when the concentration of your anion is equal to your acid, and this is known as the half equivalence point. Okay, so if you're given a pH curve and you're asked to find the pKa of the acid or the Ka of the acid, look for the half reaction point. And there you know that the pH is equal to the pKa. This is pH, by the way, over here, and this is volume of base added. Sorry, I probably should have said that sooner. All right. Similarly to the sorry, just moving on. All right, so now let's take a look at titration curves. And it's important to know some of the characteristics of these curves. If I have a strong acid titrated with a strong base, again, pH, and this will be the volume of the base added, your curve is going to look like this, with this being about 1, this being about 13. All right, your equivalence point is going to be at 7 pH. All right, and that's true for any strong acid, strong base. Okay, if I take a minute and look at a weak acid, strong base, okay, this part of the curve, if I have my pH of 1, pH of 13, it's going to start somewhere above it. You're still going to get that curve, and because it's a strong base rounding it out, you are going to go all the way up to that. All right, your equivalence point is going to be greater than 7, and that's because of the equilibrium that's set up. All right, again, this is your buffered region here. Okay, and you can find your half equivalence point and relate that to pKa. Okay, indicators. Okay, you're going to choose the indicator so that it changes color in the range of the equivalence point. Equivalence point. Okay. So for here, a indicator should have a pKin about 9.6. Okay, something greater than 7. And the last curve to look at is a strong acid being used to titrate strong acid titrated with a weak base. Again, pH, this would be the volume of the base added. pH of 1, pH of 13, strong acid, so it's going to go like that, but then you're going to kind of curve. And this should be lower than what I drew. I don't know if that's any different, but anyway, the equivalence point will then be less than 7 at a pH less than 7. And that actually concludes the acid-base series of screencasts.